Hello, my name is Andrea Pincetti and I'm a PhD student at Arizona State University. I will be demonstrating the EMS platform that we've developed as part of the NHS-THS funding project titled A Verifiable Framework for Cyber-Physical Attacks and Countermeasures in a Resilient Electric Power Grid, which was led by Dr. Alita Shankar, Dr. Oliver Kossa, and Dr. Corey Hedman at Arizona State. So the graphical user interface is a web app which can be accessed using any browser, while the actual computations are run on a remote server. Here we can see the starting menu, which allows you to select the system that you want to work with. And at the moment we've implemented 4 different systems varying in size and complexity. So we go from the 24-bus system to the Cascadia system, which is a synthetic system on the footprint of the state of Washington. And then we have the Polish test case, as well as the Texas synthetic system. So in this case, let's select the Texas synthetic system, and then we choose to display the full graph, and then we load our model. So this is the graph of the synthetic system on the footprint of the state of Texas, which was developed at Texas A&M. And we can see that all buses are plotted according to their GPS coordinates, so you can actually see the shape of the state of Texas. And we have, for example, like main cities like Dallas up here, Houston, and so on. So on this map, we have all of the traditional controls, such as zooming in and out, as well as panning. But we can also explore the map in a couple of more advanced ways. The first thing that we can do is actually to filter the components based on their characteristics, and we can search for them or change their size and color on the map. So for example, if we want to find all buses that are 300 kV or higher, we just write here voltage level greater than 300, and then we change the color, let's pick red for now, and then we make the node size much larger so we can see them. And then if we click update the graph, so we can see here that all of the nodes and branches that are rated at 300 kV or higher are highlighted here in red. So another thing that we can do is actually just click on any element, so be that a bus or a branch, and it shows us all of its info and data. So for a bus, for example, we can see its name, its voltage level, if there is any generation or loads at that bus, as well as other properties and the telemetry, meaning the SCADA measurements for this bus. And similarly for a branch, if we click on it, we can see its name, the from bus and to bus, as well as the power flow, both active and reactive power at the two ends. So we have several other functions, such as uploading and downloading specific sets of measurements, as well as downloading detailed reports, which can be really useful in understanding the system state and the operational decisions of the EMS. But for now, I just want to focus on the main application for this platform, which is simulating a complete energy management system and to observe the effects of cyber attacks on it. So if we click on simulation, we get the EMS panel with all of its core functionalities. So the bottom block here is representing the physical system, where we run AC power flow to obtain the SCADA measurements. Then we have state estimation and the traditional bad data detector, which performs a chi-square test on the measurement residues. And then following that, we have the real-time contingency analysis and the security constrained economic dispatch. So these are all the normal blocks which are present in a traditional EMS. But in addition to that, we also have the ability to perform a false data injection attack. And then we have a new block that we designed, which represents the machine learning based detector. So to understand how the platform works, we will simulate the process of performing an FDI attack, and we will observe its consequences on the EMS and on the system. So first we run power flow as a way to simulate the physical system, and we collect the measurements. So we just click on the block and we can run, and it turns green, meaning that it's successfully run. After this, we run state estimation on the measurements that we just generated, and we can see that no bad data will be detected. So it takes a second because it's a large system. And so here we can see that both detectors turn green, meaning that no bad data was detected. So after this, the estimated states are used to run contingency analysis. So here we click on the contingency analysis block and it runs. And what we're doing here is we're basically simulating over 2,700 contingencies by removing one branch at a time and then running a C power flow to identify any possible violations. So in this case, we can see that we have 24 warnings, meaning there's 24 lines that are close to their limit but don't exceed it, and only one violation. But in this case, the violation is very, very small, only 0.14% over the line rating. So after this, we can run SCAD and we can see that there is a small generation change, but nothing major. So at this point, we want to simulate our FDI attack. So what we do is we run the SCADA system again, but now we also inject the false measurements, which the attacker can compute offline. So if we run state estimation on these malicious measurements, we will be able to see that the traditional bad data detector does not find anything wrong. And we can see here it turned green. And that's because, as we described in the paper, these attacks are actually unobservable to traditional state estimation, so that the operator would not be aware of anything being wrong. But we can also see that the detector that we designed is able to flag the presence of an attack. And that's why our proposed attack detector should be implemented within an EMS. But for now, let's just see what would happen on a normal EMS, which doesn't detect the attack. And so what would happen, we just simply again run RTCA on the false measurements, which again would show that nothing is wrong, because what the attack is doing is basically to modify or change slightly the value of some of the loads, but it still represents a realistic and a normal state. So now if we run SCAD, the system will redispatch some generation to reflect the changes in loads and to get back to the most economical operating point. So we can see in this case there's a bigger change in generation, again because it has to match the change in loads. But in reality, the loads didn't actually change. So now there is a mismatch between the real loads and this new redispatch schedule. And the operator is not able to observe this because of the false measurements that we've injected. So to see what is actually happening on the system, what we can do is to reset the loads to their actual values. So we just click here. And now we run contingency analysis with this new generation dispatch and the real loads. And so what we find now is that there is actually a very large violation, meaning that one of the lines would have a flow of over 112% its maximum rating, and the control center is completely blind to it. So this was an overview of the basic functions of our EMS platform and how FDI attacks are performed. But as we explained in the paper, the user interface that we designed actually allows us to access very low-level functions, as well as to get insights on all of the algorithms we implemented. So for example, here, for each block, we have different options that we can set, and we can also analyze the results more in detail. For example, for contingency analysis, we can see a complete list of all of the possible contingencies and their violations. As well as for SCAD, for example, we have different options that we can select, and we can see in detail the results in terms of generation dispatch. And so this is why our platform is actually such a powerful and flexible tool, and it can be used for many different power system studies. So to conclude, I would like to thank you for your attention, and if you're interested in learning more about our work, you can find our contacts as well as supplementary documentation in the description below. Thank you.